Hi, in this video we're going to look at something called level notional swaps. In the last video we looked at general swaps and in particular interest rate swaps. And now a level notional swap will be a special case in this interest rate swap framework that I expect that you'll, if you see a swap problem on the exam, it will likely be in this situation. Okay, so let me remind you of an interest rate swap. It's a swap in which the payments are all interest amounts, and the interest amounts then are the interest amounts are based off of forward rates that are not equal to each other, and you want to swap that for a set of payments where the forward rates are all equal to each other. In other words, and we use an I for what those forward rates are. And so in other words, we're swapping a non-level yield curve for a level yield curve. And we do this in a fair way, and a fair way is that the present value of the two sets of payments are equal to each other. So I'm using a three-payment example. It could be more than three payments, but I'm just using a three-payment example at this point. And so if I take the present value of each of these payments, we're in the context of a term structure of interest rates. That's why you see those forward rates in there. And so I have to use the extra decorations on my V's, a V sub 2 squared, a V sub 3 cubed, and so forth as my discount factors. And so the present, when I set the present values of these two payments, sets of payments equal to each other, this is what I get. And I generally solve for the interest rate I, the swap rate I, and I do that by taking the expression on the bottom right, factoring out an I, and then dividing by everything that's left over, and that's what I'll get. That's what the swap rate is. Okay, so that's the idea behind a interest rate swap, and now we're going to talk about a level notional swap. Well, the level notional swap, look at the words level notional. That means that the notional amounts are all going to be equal to each other. And so I'll highlight in red what the notional amounts are. The notional amount at time 0, at time 1, time 2. They're all equal to each other, so I don't need the extra decorations. I'll just put an N in for everything. And notice that when I do that, look at the swap rate, look at the expression I get that defines the swap rate. All those N's are just going to cancel out from one another. So when I factor out all those N's, cancel off, I just get this formula for the swap rate. So that's going to be my formula for a swap rate for a level notional swap. Now let me make a comment here. The rest of the video is intended to show you a way to reduce this formula to a very nice, easier formula to memorize. Okay, so what I want to do is I want to focus on the expressions in the numerator. Notice every term in the numerator is the product of a forward rate times its corresponding periodic discount factor times its corresponding V. So let's take the middle one, for instance, and look at it look at it more closely. Let's look at the forward rate from time 1 to time 2. Let's start with that expression. Well, to get the forward rate from time 1 to time 2, I do that by using the spot rate from time 0 to time 2 and the spot rate from time 0 to time 1. So this is my picture to get the forward rate from time 1 to time 2. I can accumulate directly from time 0 to time 2 using a 1 plus S sub 2 squared, or I could accumulate from time 0 to time 1 using a 1 plus the 1 year spot rate, and then take that and accumulate it from time 1 to time 2 by taking 1 plus the forward rate. So when I solve for the forward rate in this equation, I would do so by dividing both sides of this equation by 1 plus S sub 1, and then subtract 1, and that's what I get for the forward rate. So let me take out the timeline, get a little bit more room, and move the formula for the forward rate up. So that's what the forward rate is. That's my formula for forward rate. But look at the middle expression. I'm going to take that forward rate and multiply it by the corresponding discount factor. This is a forward rate from time 1 to time 2, so it's a time 2 value. I discount it back to time 0 by multiplying by a V sub 2 squared. So when I do that, all I did is multiply that expression times a V sub 2 squared. But now let me highlight in blue a couple of things. So the numerator of what's in the first term that's in brackets is a 1 plus S sub 2 squared. And then look at, I'm multiplying that. I'm eventually going to be multiplying that, and when I distribute the V sub 2 squared, I'll be multiplying by a V sub 2 squared, which is the reciprocal of it. And so when I distribute that V sub 2 squared across, the V sub 2 squared times the numerator in blue there in brackets, that product just gives me a 1. So I'm left with just a 1 over the 1 plus S sub 1, and that 1 over the 1 plus S sub 1 is the V value with respect to a 1 year spot rate. So that's a V sub 1. And so that's my punchline here. So let me just take out the intermediate steps. That's the punchline. Let me show you the, let's look at the third term in the numerator, and then you'll be able, I think, to see what the pattern is. So let's look at the third term, and let's first recognize that just the forward rate by itself from time 2 to time 3 is given by that expression. So I'm going to want to multiply that times a v sub 3 cubed, and when I do so, look, the numerator in the first term in the brackets, I'll put them in blue again. When I distribute there, the things in blue there are going to multiply together to give me a 1. They're reciprocals of one another. The 1 plus s sub 3 cubed is the reciprocal of the v sub 3 cubed. So when I multiply those together after distributing the v sub 3 cubed across the brackets, when I multiply, I just get a 1. So I get a 1 over the 1 plus s sub 2 squared. But the 1 over... that's my first term. The 1 over the 1 plus s sub 2 squared is nothing but the v sub 2 squared. So I just get v sub 2 squared minus a v sub 3 cubed as the expression for that product. So let me, again, clean it up. So now I think you can kind of see what the pattern would be here. And now let's look at the very first term. I'm going to back it up. And if I just follow the pattern that I have here, the forward rate from time 0 to 1 times a v sub 1 would be a v sub 0 to the 0 minus a v sub 1. You can, that's true as long as we define the v sub 0 to the 0 power to be 1. And so v sub 0, I'm not even sure what v sub 0 really means. It says 0 your spot rate. I'm not sure what that is, but I'm thinking of raising it to the 0 power, and when I do so, I'm going to get 1. And that's my justification of setting that equal to 1. And so, so the first term in the numerator of the expression for the I for the swap rate would be a 1 minus a v sub 1. Okay, so this is these last three formulas are very useful to see that pattern and to use it. I'm going to come back to that again in a later video, how if you'll do some things symbolically, if you'll do some calculations, symbolic calculations first, you'll get to a point where your numeric computations are less tedious to do. So that's the situation that we're in right now. For instance, look at the swap rate that I have written right now, the expression for the swap rate that I have written right now. That's I equals, and then that numerator divided by the denominator. If I were to give you numeric values for the 1-year spot rate, the 2-year spot rate, and a 3-year spot rate, you could actually go through and just calculate the numeric values of all of those factors and all of those terms in that expression for I. However, if you'll take it a step further, symbolically, you'll see where you'll get a much easier, less tedious expression to numerically evaluate. So let's talk about that. I'll put in brackets. I didn't change anything. I'll go back to the previous slide here. I'm just going to put some extraneous brackets in the numerator for this expression for I. It's not going to change anything. It's just I want to focus on these, and I'll do so by color coding things. The first bracket I'll put in red, and I'm going to substitute in what's in red. I'm going to substitute in there a 1 minus a v sub 1. What's in blue in the second brackets, I'm going to substitute in a v sub 1 minus a v sub 2 squared. And what's in black in the third brackets, I'm going to substitute in a v sub 2 squared minus a v sub 3 cubed. And when I do that, this is what I get in the numerator. And what I've been saying is, if you'll go through this symbolic calculation first, or computation first, you'll see the numerator. Look what's in the numerator. It's a telescoping sum. The v sub 1s add out, the v sub 2 squares add out, and so I'm just left with a 1 minus a v sub 3 cubed divided by what was in the denominator to begin with. Okay, so that's and then that's a much easier calculation numerically. When I give you, now when I give you the term structure of interest rates, and I give you the 1-year spot rate, 2-year spot rate, 3-year spot rate, this is a much easier calculation to do than if you would not have done the symbolic calculations first. And for a lot of you, you're just going to memorize this particular formula, but I want you to know where it came from, because it is useful in other settings to see the product of this forward rate times its periodic discount factor just becomes the difference of these V's, the corresponding V's. Okay, this is so useful though. I want to show you one more. I want to take it one step further, and I want to do so by putting in an extra 4th year on our payments here. So if I had an extra 4th year, that's what the timeline would look like. I want to swap the payments that have the forward rates, payments based off forward rates, to payments based off of a fixed interest rate I, and I want to do so in a fair way. And a fair way means I take the present value at time 0 of these payments. What I have on the screen would be the present value of the payments that are based off of the term structure of interest rates. That's not level. That's a non-level, based on a non-level yield curve. And on the right-hand side, what I have is the present value of the payments that are based off of that fixed interest rate I. All right. Once again, you'll see that if you have level notional amounts, this is very important. If you have level notional amounts, then I won't depend. The swap rate will not depend on that cap-in value. The cap-in value is just going to cancel off. And I put in brackets there. Notice that the first set of brackets, I'm going to replace that with a 1 minus a v sub 1. The second set of brackets, I'm going to replace with a v sub 1 minus a v sub 2 squared, and so on. And when I do that, in the numerator, I get a telescoping sum. And so the swap rate just reduces to this expression in the numerator just reduces to a 1 minus a v sub 4 to the 4th power. Okay, so let me box off that formula. That's a good formula to know, and if you want to commit that to memory, that's fine. It's not hard to derive that formula if you'll remember this other formula that so the bottom formula is the one I think that is more important. The bottom formula has applications in more problems than just this particular problem, and so I would suggest you memorize the bottom formula, which is that the forward rate. If you take a forward rate and multiply it by its appropriate discount factor, it just becomes a difference of these two different discount factors. Okay, so I will see you in the next video.